before I forget, I always forget this. I'm also with Fraunhofer ISAC, so this is a German security institute, the AI department head. So I think it's important for collaboration issues, right? Because it's very different, Fraunhofer and university. So the talk is about bilinear compressive security. So if you look that term up, you won't find it except for one paper, which is on arXiv. So you can read this, what I'm presenting here in short. In this paper on arXiv, and this is joint work with Axel Flint, so he is at Umeå University in Sweden. Oliki, he's a guy from Poland, Warsaw University, and Simira, he happens to be a PhD student of mine, but in the crypto field. So she's not really with finite fields. So this is about not finite fields, it's about vector spaces over C or, yeah, over C. And as a matter of fact, so it's a short version of this ICC26 in Glasgow paper. Okay, so what is this about? Okay, a very old term, compressed sensing. You probably all have heard of this. It's still something that is there in the community, and probably it's implemented in practice many times. I'm not going through it in detail, but you can see the main idea is it's about how to efficiently compress signals when the signals are structured. And the structure is given by sparsity in some known basis, right? And what you do is you take, for example, an image, it can be anything, right? It can be, time series, image, audio, whatever. But if you take an image and then do a measurement, the measurement is not, you pick certain pixels, you do random projections onto C. And then you have a measurement, and then you recover it by saying that within the structured description of the actual image in some known basis, the representation is sparse, and you get from this, sparse representation, the reconstructed image, almost, with no errors, which is quite good because there is a big compression, and also you can, from these small, small dimensional measurements, you can reconstruct everything, and you can also change, the viewpoint, the angle. You can do everything what you want, so that there is no loss. This has, this is used in image processing quite a lot. It has a lot of application also in machine learning, right? So several networks. Convolution networks. So just look it up. You will see that this is actually a sparse encoding problem with some unknown basis, right? Good. So that's the mathematical description. Everybody's probably familiar with this. So it's kind of boring. So you have a measurement matrix, and just let us clarify the nomenclature. So you have a measurement matrix Q. You have some S-bar signal, and this happens to be the message later on. And this Q is some kind of random matrix, so typically taken from some IID Gaussian measurements. So it has to have some properties. I just forget about all of this, and then you have a vector of measurements, which happens to be then the ciphertext later on. So the reconstruction can be done, this famous L1 problem, so which solves a problem not in L2 but in L1. So it picks the spiky parts of the signal, so that's why it becomes sparse naturally, and so on and so forth. And you can also, 1,000,001 greedy algorithms to solve this problem. Okay, so let me come to my main point, which is the story. So the story is that, as a matter of fact, it's a bit of, physical layer security, because you can set this scheme into a security setting, which is then called compressive security. That's a term which exists. There is a book about it, or more books meanwhile. So here the observation is, so Q is a random matrix, and then these measurements are naturally equipped with some, security. And so you consider this Q as a secret key. can be huge, right? Because it's a matrix. Typically, well, it's over C, right? So there's no natural quantization, which makes this a bit interesting for the classical cryptographic community. I have to say this, and this is the usual problem with physical layer security anyway. So I'm not alone here. But so you encrypt with Q times X, and that's a ciphertext, and then you recover, and that's the deciphering. So this is attractive. Why? Because it's resource limited in settings. You kind of save compute, you save memory, and you save sometimes energy, which often is set as the main motivation for this. And also, so if you change for every message this Q and pick it random again, then it's also perfectly secure modulo the energy of the signal. Right? So if you put some information in the energy of the signal, it might be a bit of a problem, but it's still computational feasible, because it's very hard, if you don't know anything about Q, very hard to recover. Good. So I looked it up for this paper and found this one here. I'm not saying, I'm writing papers about physical layer security, but I'm always saying there is no practical scheme. So maybe, Igor, you know one, I don't know. But I don't know any scheme that has been implemented in practice. We talked with Bosch some 5 years ago or 7, but I don't think they have actually ever done it. So I found this paper who uses this compressive sensing method for secure and energy efficient ECG signal transmission application. This is quite new. So from May 25. And you see it's exactly the scheme that we just had described. So you have a compressed sensing encoder, you have compressed sensing decoder, and so on. It's applied on these sparse signals. And you see you have actually 2 encryption levels. One is, the Q. So the number is a bit, I just copied that, that image. And by the way, sorry for PowerPoint. So I don't know why Samira sent me PowerPoint. I've really had a hard time to amend it sometimes. So you see it's a bit different. So it's not the Q, but it's the phi, but anyway. And there's encryption level 2, and that is why. Because, of course, if you change the matrix every time, when you, like a one-time pad, then you're fine. But this is totally impractical. Otherwise, you would, implement a one-time pad anyway in the practical system. So it's not done. So what you usually do, you do some kind of noisification on top, and this is the column permutation, which you also have to, communicate. So it's also part of the key. And this is the main problem, I think, with this compressive security. So I mentioned already this, one-time pad behavior, but because, if the Q is actually fixed over some time, it's very easy to reconstruct, particularly over C, right? So because you just need to choose this plain text attack, or even have a known plain text attack, which doesn't really matter here, but it's just that you know what has been sent over some time. You collect the measurements, by linear algebra. You just invert this matrix A, and you get the key. So, and it's broken. So the question is what to do with this. So is it still interesting? That's the question. So as we just saw from this other paper, so you do some tricks, and there are many tricks to do this and to improve this, because it has still, this flavor of potential and properties which make it amenable for practical systems, particularly in this IoT setting, right? So what you usually do then, and this is very similar to cryptography settings. So I mentioned here LPN. This is to recover a linear equation or parity linear equation with noise on finite fields. And this is very difficult and different, because if you do all this, what I'm just saying, over finite fields, and you don't know the actual encoder, you have a random decodability problem. This is known to be NP hard, right? So McAlee's scheme on post-quantum crypto is actually using this. So how could this look like here? And that's why we came up with this scheme. So what we do is this, and we call it bilinear compressive security. It's done, so you still have the Q, the measurement, And the Q is not known, so it's secret, the secret key, and it's fixed, maybe fixed for some time. But then it's anytime you send a message, you're convolving with some channel H. And if you think of it, so if H is, fully equipped, so it has no sparsity, well, you might intuitively say, yeah, so the message is covered completely, right? Which is good for Eve, but for Bob not, right? Because he cannot recover. So what you typically do is you make the message X sparse, you make the channel sparse. And where the coefficients actually in H lie, it doesn't really matter. So this is 4x. So it's not some, subspace. So it's the manifold of subspaces, but it's sparse. And then, Eve doesn't know H, he doesn't know Q. And the question is, what can he recover? And also the question is, what can Bob recover under what conditions? Right. So I don't know if you have ever heard of this term. I couldn't find anything about it. So because this is sometimes, it's a bit funny because it's a very natural next step. So you kind of distort your transmission in a way that Bob can recover and Eve not, right? And there's, of course, a certain trade-off. You might expect over time you can recover, but definitely Eve's work has become harder, right? Because he now not only has to recover Q, but he also has to H. And the manifold of the ciphertext looks very complicated, undescribable, of course. So actually, we have used this. So if you might have a look, it's also an archive that was from last year, transaction information forensics, where we actually used this recoverability and unrecoverability of this scheme in some very specific setting. But I guess because you're very hard with time, I'm not saying anything about it. So I have until 20 minutes after, right? So still 15 minutes. Is that correct? Because okay. We'll start a bit later. Okay, anyway, so that's the scheme. As I said, so the encryption is done, so you have a secret key and you have a public distribution of H of the channel. This is all known, but then you have a secret message. It happens to be sparse. You have a secret random filter H, which is also sparse. You compute the ciphertext H convolved with Q times X and send the ciphertext to Bob, and Eve can overhear it. And the decryption goes like this. So secret key Q knows the public distribution. Bob receives Y and solves H convolves with Q times X for both H and X with a blind deconvolution problem. Okay. Good. And you see that's the image from the paper. So far, Eve has all the potential that he wants. There is no limitation. Good. So one first theorem. It's very also from last year. The question is whether Bob, under what circumstances Bob can actually recover the message and the channel from the ciphertext. And you see it has this here. So we need this sparsity. So we have a constant K. You see this, the number of measurements has to be larger than K times S times sigma. And S is the sparsity of the message, and sigma is the sparsity of H. And then some polylog factor of N and M. And this polylog factor is logarithmic, of course, in N. And it means that this is kind of the rate penalty that you get. So instead of submitting, one symbol per dimension, you can only send one symbol per one divided by log something per dimension, right? So it grows with N, but only logarithmically. So this is a rate penalty which always is there in compressed sensing and also is inherited, by the bilinear scheme. But it is a very efficient algorithm. It's called a hierarchical HTP. So it's a hard thresholding Percy algorithm, which is hierarchical. So you might ask how this works. So actually, the convolution is written as some kind of deterministic measurement operator times the Kronecker product of H and X. And the funny thing is that this deterministic measurement operator has this the right properties like RIP, etc., with some probability. And that is why it works. Also, even for the hard thresholding Percy variant, because this is a hard, threshold. And this is very funny because it's really nonlinear and non-continuous that this actually works. So you can recover it. So Bob, under this assumption, of course, you see if the sparsity grows in S and sigma, you see you need more measurements. So which contributes to the rate penalty. Good. So now turning to Eve, and that's the main contribution of the paper. So that is, as I said, this I might have not said it. So this is just published in the mathematical journal. So it's really technical, but here the point is on the security analysis. So it's an attack model that we use, and here observes, again, like a plaintext, known plaintext attack. So it observes plaintext ciphertext pairs xk and yk. And for any known xk, it also observes many yk. And this is even, more to the benefit of Eve. So the message stays constant for some time. So why? So that he actually can figure out the distribution of H over time. So we really give him even more benefit to this. So all this is not, of course, really practical, but these are all the benefits for Eve. So when we prove something, it's under this, it has to be viewed under this, quite general conditions. Eve knows everything in this, so knowledge of filter distribution, etc. So intuitively, he wants to figure out the distribution of H. So where in this complicated manifold is the distribution, and get some over H. And then from this, you figure it out, okay, what is the distribution, calculating which actually key was used. Good. So keep in mind, this is very favorable for Eve. And then carrying out these security analysis, we have this. So first of all, there is some ambiguity anyway, so which cannot be resolved. So the message X and the key Q will lead to the same ciphertext, when you multiply it with some unit complex number theta, and divide this at the same time Q by this theta, right? So that's why we came up with this definition. One, recoverability. So we say, first of all, PU is the space of equivalent classes in some vector space U, modulo the unique scalars, right? Complex scalars. So U and V are lying in the same equivalence class. If U, it can be written as theta times V for some theta in C with magnitude equal to 1. So in the actual recoverability task is this. So that H have a known distribution, calligraphic D. So we say that a set of vectors xk, k is over M, uppercase M measurements in Cn, can retrieve the key for distributed H if the map Q, so the key, from this equivalent class of Cm times n to the set of probability distributions, right? Because everything is, random. We need to figure out this is that distribution, this is that, and this is connected to the key, so and so and so. Okay. So that's the basic definition, how we want to define this recoverability. And I have to say this, if this, we say it can retrieve it if this mapping is injective. So, and you might say, we heard a couple of results here today. This is not information theoretic security, of course. This is just injectivity. It's very weak, I know, but the problem is very hard, right? So this is just a starting point, how to qualify and quantify what's going on. Okay, so we have two cases. One is the IID Gaussian case as an illustrative case. And you're maybe not surprised for IID normal Gaussian filters. No set of vectors xk, k in uppercase M measurements can retrieve the key. And this is easily seen. So if you go through it, this is very nicely described in the paper. As a matter of fact, the attack can be described, constructively. And it turns out the problem separates into M independent phase retrieval problems, right? And it also turns out that these phase retrieval problems can actually be solved for each column of these secret key matrix, but it gets, an independent phase factor for any of these columns. And that is why the scheme is secure for the IID normal Gaussian filters, let alone, needless to say, Bob would never be recovering this because it's just counting the number of dimension, it's impossible. So the phase retrieval problems meet, so we take the same set of vectors, xk, k in uppercase M measurements, and we say, it is solving the phase, this set solves the phase retrieval problem if it, recovers, and this is the Q, but it should actually recover the whole key with, modulo this equivalent class. Okay, so I have to hurry up a little bit. So that is all fine. It gives some insight just for illustrative purposes. The second thing I just want to say is then we turned into something which is more general with a slight constraint. So we say it's a phase symmetric case. So the H, the channel H, has to be like, so if you have some tether times H, it should be still equally distributed as H. This makes a lot of sense, and many mobile channels have this this characteristic. Nevertheless, of course, it's a mathematical assumption. And then you see our lemma means, so actually we can recover the modulo the equivalent class exactly if Q and Q times xk of k in uppercase M measurements is an injective mapping. Okay, and here's the technical main result, and this is quite involved. The others are all mathematicians that are involved in the paper. And this is the main technical result. And for a set of vectors, the map phi from lemma 3 is injective if and only if the vectors xk, k in uppercase M, can do phase retrieval. And you see here, the main observation, I just want to pinpoint it for you, H is non-existent anymore, right? There's no H, right? So we have, brought down this problem without having to define what the action of H is. And this is the main technical result. So this is a longer proof and quite involved, but the theorem 5 is again in the paper because it's just a kind of a corollary. And this is a constructive result. It says two things. So if the message, we're assuming recoverability, so H, sigma, and S are the number of measurements are taken so that you can recover. But if you take the special case that the message of X is equal to 1, the mapping is never injective. That's one thing. I'm coming back to this result in a second. And the other one is if M, the mapping is injective, if the number of measurements is just take the first part here. The other one is classic phase retrieval. This one here, if it is like on the order of n squared divided by s squared, which means if we have a message, I'm done in a second. If you have a message which is sparse over n dimension, right? You need at least n squared under this very beneficial assumption on Eve measurements to achieve at all, injectivity, right? And this S equal to 1 is quite interesting because I thought, wow, this looks very good. So we take this assumption, and maybe it even beats Shannon because it means that you can always, cover your message within the transmission, and then, right, you don't have to report or change Q at all. This would actually violate finite dimension channel theory, you know, one of his security theorem. But it's not as easy, so we can discuss later on. But you see, actually, the injectivity result looks quite nice. So this is always, you know, this part here. So when S is equal to 1, it means that it never recovers over, it's a kind of error with some threshold. And this error always, explodes over the threshold if you, regardless of the number of measurements. So this x-axis is the number of measurements. So quite nice. So the theory is fine. And then if you increase S, you are partly, sometimes you recover within some margins. So this depends, of course, on the threshold, etc. And if S and sigma grow, you see you're always getting better and better. Good. So last slide, I'm done. So that's the main issue. So Q will be perfectly skewed the message I want, but we were not able to design a proper scheme with S equal to 1. So it's even Bob has to send some real information was not really clear how to do this. And you see n and n squared is exactly the guaranteed ratio that you can achieve theoretically if you want injectivity, which is not perfect security, of course, but it's something. Not much, something. That's it.
Thank you very much. Are there questions? Doesn't look.
So I did not understand in the end what security definition do you take? Is it in CPA secured?
Yeah, the attack is known plain text. So we know, okay, this message has been sent. So we collect the measurements where we know what XK is, right? And we have uppercase M measurements. And from there we can recover. So we know what, two parts of the equation, and we want to recover the key Q. And in the bilinear scheme also H, right? And then the question is, how can we do this? And it's just an injectivity result. It means that 2Q map onto the same point, right? And then we say, of course, you cannot recover Q because it has, multiple choices. The question, of course, is how often does this actually happen in the practical system when you take random samples of Q? So how often does this actually happen? We don't. That's a problem of this definition of security, right? But we see in this, that's why the simulations are definitely encouraging, and it's really low cost. You can just put it on top. It's even, in any case, better than the classical compressive security scheme, right? So, yeah. But I totally understand it's not information theory, so it's an injectivity result. Just say, okay, so you cannot recover Q because they point to the same output.
Another short question.
Thank you very much for the interesting talk. I'm curious whether the compressive security can be related to the hash function or leftover hash lemma. The operation looks similar, and maybe we can use this collision probability or collision entropy to characterize this attacking or this whether the probability of successfully attacking things like this.
Maybe, but the hash over what is it called? Leftover hash lemma. This is over finite fields only, isn't it?
As far as I know, yes.
So this is a big problem here. This makes it always easier for the attacker because we're working in vector spaces over C, and we are not, randomly going outside. So we have some modulo stuff like in finite fields, which creates all these, this randomness, which in the end you have a hard time to recover. So this is not happening. And so I'm taking up this comment. Let's see. But I know the dilemma and the different mathematics is used here and needed so far.
Thank you.
Okay, let's thank Professor Wunder again.